Okay, welcome everyone. This is the lecture about restricted Boltzmann machines. So by now you would have hopefully seen the lecture on Hopfield networks. And this lecture is kind of a carry-on from that. It uses some of the same concepts. And in fact, as you can see here, the restricted Boltzmann machine, basically it was involved in the Nobel Prize in physics that Hopfield received. Hopfield and Geoff Hinton both received the Nobel Prize in 2024 for their work. So this is kind of Hinton was using some of the same concepts that Hopfield was using. So a restricted Boltzmann machine is similar to a Hopfield network, except it's split into layers of nodes. So the two layers are fully connected and they form a bipartite graph. So let me draw that. You've got, first of all, you've got the visible nodes here. I'll draw a few of them. 1, 2, 3. And you've got hidden nodes. I'll number them 1 and 2. And they're fully connected. Is that fully connected? Yeah. So this first bottom layer is called the visible layer. And it's called visible because it's basically exposed to the input. So input comes in here. So it's visible in the sense that your retina is input to your visual system, and it's visible to an optometrist. Now up here is the hidden layer. So I'll refer to the visible layer as V, a vector V, and the hidden layer as H. And the connections between them I'll refer to as W. Okay, so now we have the stages set. So let's look at how these things operate. Each node in an RBM is either on, 1, or off, as you would have seen is similar to a Hopfield network. So the probability that a node is on, though, depends on the states of the nodes feeding into it, kind of just like a Hopfield network. So, so let's just be a little bit more explicit about our nodes here. We got V1, V2, and up to V, what am I saying, VM. So we've got the visible state. We've got H is the hidden state, is a vector. H1 up to Hn. Okay. So together, the V, the visible and the hidden state represent the whole network state. And so I've given an example here where I've got 4 visible nodes and 3 hidden nodes. So together, they form a single network state. And so as the visible nodes change 1s and 0s and the hidden nodes change their values, the state of the network changes. So in this case, the state of the network is actually 7 binary values. So the total number of states would be 2 to the 7, which is 128. Okay. So now we're going to define the energy. Okay, this is like physics now, right? And we define energy from the Hopfield networks. Energy of the network is defined as, so this big formula, negative of the double sum, I goes from 1 to m. So we're adding up over all the states of the network. J goes from 1 to n. Vi weight ij times the hidden j. So this is just like the Hopfield network. You might notice that the signs are different than the Hopfield network. It's okay. I've given a lot of thought, and this way works best for our purposes here. Now this is basically, I'll fill in those. I'll label these terms in a second. I can't write and talk at the same time very well. So this first term is basically a discount. Let me write the vector version of it first. So using row vectors, we got negative v times w times h transpose, because that needs to be a column, plus what am I doing here? V times b transpose plus h times c transpose. So this first term is a discount for when nodes are both simultaneously on. When nodes I and j are both on simultaneously. You can see that if they're both on and there's a positive weight, that basically reduces the energy. If they're both on and there's a negative weight, that increases the energy. So you can see that when they're both on, we want a negative weight because there's, or yeah, we want a negative weight, positive weight. These two terms are the energy incurred by turning a node on. You can see that when you turn, well, those can be negative values too, so maybe it's better to well, no, we don't have minus ones. They can be negative, but anyway, I don't want to read too much into the values of those things. It works, okay? All right, he got the Nobel Prize, give me a break. Like many processes in nature, we want to find the minimum energy state. So how? I mean, finding the minimum energy, as you saw with Hopfield networks, involves finding all the correct values for the nodes, ones and zeros. But we don't just have to accept the connection weights and those biases, B's and C's. We can also ask, how can we choose those to reduce our weight as well? Okay, so let's consider the energy gap. What is that? It's a difference in energy when we flip a node from off to on. So let's look at node V sub k. So I'm going to call it delta sub k. No, I'm calling it delta E sub k. It's going to be the energy with V sub k off minus the energy with V sub k on. So if you look at the energy formula, when V sub k is off, the V sub k is 0. When it's on, it's equal to 1. So in the end, what you end up with is a sum over j, wkj times hj, minus bk. And so this is just input current. Like that formula should look familiar. That's the sort of thing we would do, multiply the presynaptic neurons times the activity times their weight, and then add or subtract a bias. So this model is already like the Hopfield network, looking like what a neural network can do. Okay, so with this energy gap, if the energy gap is positive, that means the energy for V sub k being off is higher. So in other words, V sub k being on is a lower energy state. So in that case, we'd want to say, we'd want to set V sub k equal to 1 to be on. If it's negative, if the energy gap is negative, then it's the other way around, right? Energy of V sub k off is less than energy V sub k on, so we'd want V sub k to be 0. So this is the choosing the V's to minimize, choosing the activity of the nodes to reduce the energy, just like we saw in Hopfield network. So we're fixing the weights, but changing the activities of the neurons. And you could do the same thing for the H nodes, but I won't bother writing it all out. So the energy gap of each node depends on the states of the other nodes, right? Because as we saw, that's the formula. It's like an input current. So one strategy is to visit and update all the nodes in random order, like Hopfield. We can do better since our network is bipartite. Remember, way up here, it's a bipartite graph. So the V's don't talk to each other directly, and the H's don't talk to each other directly. It's got a special structure, and that's why it's called a restricted Boltzmann machine. We'll get to the Boltzmann part later. The visible units only depend on the hidden units, and the hidden units only depend on the visible units. So we can update a whole layer at a time. That's what we do. Okay, so however, this is still a local optimization method. In terms of finding the values of the V's and the values of the H's, it's still a local optimization method. And so you might get stuck in a crappy suboptimal local min. It's still a local optimization method. And so we could still get stuck in suboptimal local mins. So to help avoid that, we use stochastic neurons. So these neurons don't just flip on and off according to the input and just a threshold. Instead, the input current is fed into a distribution. So the probability that V sub k is on, given all the H's, is going to be logistic function applied to the energy gap. And the probability that H sub j is on, given all the V's, is going to be also the energy gap for that hidden neuron. And so just to remind you what the logistic function looks like. So this sigma is meant to be the logistic function. 1 over 1 plus e to the minus z. And I'm going to put a t in there. That t represents temperature. So logistic. That t represents temperature, and here's what the effect that temperature has. Here I'm showing a bunch of logistic plots here. Now as you turn the temperature up, it affects the slope of the curve. So turning the temperature up, you flatten out that logistic function. So this is for large T, and it represents a hot. I'll get to the physics in a second. And this smaller t stands for cold. Whoops. So I guess I can go down here. So the idea here is it comes from statistical mechanics. So these neurons are sort of switching states between 1 and 0 using this probability. So this up here is basically a Bernoulli process where, given the energy gap, which is basically the input current, run it through the logistic function, you get a number between 0 and 1. That is the probability that neuron is on. So this is a Bernoulli process. Each neuron is following a Bernoulli process, and the probability for its being on is dictated by the input. So all these little Bernoulli processes are flipping off and on, and they're influencing each other. So this comes from physics. It comes from statistical mechanics. So suppose that particles can be in one of two states, 0 or 1, and that the energy difference between the states is delta E. This is a very physical concept. Changing when a particle changes its state, it incurs an energy cost. But they influence each other. So P is the fraction of particles in state 1. So as the temperature increases, there's more and more movement back and forth. So when you increase the temperature of something, basically it's more dynamic and more things are changing. When you turn the temperature down, the particles move less and they become more fixed and less likely to change. So that's why in this model, a hot temperature, the particles move a lot, and it flattens that logistic curve. So for example here, if we have this particular energy gap, then looks like there's an 80% chance that the neuron will be on, and a 20% chance it'll be off. And so as you increase the temperature, that 80 will drop down to like 70, and if you decrease the temperature, that curve will get more steep, and that percent of that'll be on will climb up towards 1. Okay, so it's got to do with these particles changing state, and these particles are Bernoulli processes that, and you can measure the energy. So given that we have this Bernoulli process, each neuron is on or off according to this probability that is established by its input current. You can then compute, do this like Bernoulli process in the computer. So if you want to figure out the probability that neuron H sub j is on, you basically evaluate its input, run it through the logistic function, which gives you a number. And so I'll call that number H, capital H here. Capital H is that logistic. Trying to undo. Yeah, whenever I undo in OneNote, it jumps around. I hate that. Okay, so I've computed it for all those H neurons, and now I'm going to loop through them for j equals 1 to n. I choose a random number, and if that H sub j is greater than the random number, I turn the neuron on. If it's less than the random number, I turn it off. So this gives me a vector of 1s and 0s that represent the binary hidden state. So you could do the same thing for the visible nodes as well. Bernoulli process. Okay. So this little box here, this is basically a Bernoulli process. We're sampling this Bernoulli random process. If I reran that again, I get a different set of random numbers, and the neurons, the nodes might show a different pattern of on and off. But in general, though, if I run it 1 billion times, you'll find that neuron H sub j will be on the percentage of time dictated by its Bernoulli probability. Okay, so we do run it lots of times. So if we let our network run freely, it will occupy all possible network states, but not with equal probability. These neurons will be switching their states, and as they switch states, they influence the input of the other neurons, and so they're all sort of collectively changing states. So I showed you the example before where there were 128 network states, right? If you look at the binary visible states and the binary hidden states, in total there were 7 nodes, so 2 to the 7 was 128. If you run that network with this Bernoulli process, it will occupy all 127 states, but not with equal frequency. Now instead, they'll visit the network state VH with a probability given by the Boltzmann distribution. So it's 1 over z times e to the minus energy, where z is this normalizing constant. It's the sum over all v's and h's of e to the minus EVH. So this might look familiar. This is basically like the softmax. E to the whatever, e to the z divided by the sum over all the e to the z's. So if we look at this, if an energy of the state V1H1 is greater than the energy of state V2H2, then the probability of the state V1H1 will be less than the probability of V2H2. Why is that? Because it's it's little e to the minus e. So the higher the energy, well, I guess that this next line states it nicely. The lower energy states are visited more frequently. And it's all because there's a minus capital E in the exponent. So when the energy is lower, you get a higher probability. So this is known as the Boltzmann distribution. Boltzmann distribution. So I already went over this thing that it comes from physics, so we can skip over that. So if you let the restricted Boltzmann machine run freely, it will jump around from state to state, but will occupy lower energy states more frequently. So here's just a little example where I've got 3 visible nodes and 2 hidden nodes. So therefore, there are a total of 8 visible states, 4 hidden states. Multiply it together, there are 32 total states. And so I've got them all listed on the state axis here in whatever order. And this red line is the energy. And this blue line is the frequency, the visitation frequency from running a simulation. I ran it probably 10,000 times or something. So they're normalized so that they could be visible on the same graph. But you can see when the energy is low, the visitation frequency is high. Okay, now we want our neural network to represent something out in the world. So let's suppose that this neural network is walking around through some world and it doesn't see everything with equal frequency. It's what it observes follows some distribution. So the visible states that it encounters is delivered by this process that happens in the world, this distribution P. So now we want our neural network to be sensitive to that distribution. Remember, this is an unsupervised learning method. So we want our neural network to basically observe the world and then come up with a better representation of that world. Basically, statistically rule out all the things it doesn't see and focus more attention on the things that it does see. One way to do that is to come up with a generative model, Q sub theta. So Q sub theta is going to be chosen so that we maximize the expected value of the V's that we observe in the world. So we're going to sample these V's from the actual world, and we want the expected value of this Q to give us bigger values for V's we see more frequently. So basically Q sub theta, the theta is basically weights and biases that we're going to be playing with. We want Q sub theta, this neural network, to assign high probability to V's that we see more frequently in the world, and low probabilities to V's that we see rarely or never. So if you're maximizing that probability, you could also say you're minimizing the negative log of that probability. Okay, so that's what we're going to do. So let L be the negative log of that probability for a given V. So I'm going to choose a specific V out of the world, and I'm going to give it this different font. So note the font, i.e. it's not the same as that V. So this is a kind of a Greeky sort of scripted V. So that represents a fixed V that we're seeing in the world. Now we want to, we will replace the Q sub theta with our Boltzmann distribution, right? Q is basically representing the probability of observing that particular visible state. So we plug that visible state into our Bernoulli distribution. Sorry, our Boltzmann distribution. And we want this probability, if we see that particular V frequently, and we are seeing it now, we want to basically increase the probability decrease, negative log probability. So we want to minimize this. We want to decrease that Boltzmann probability. Well, we want to increase the thing inside the brackets, which will decrease the entire negative log of that thing. Okay. So it's a log. It's a log of a product, so you can split up into two pieces. And this first thing, I guess this line here comes from the fact that it's a marginal. So we have two different, like the energy was actually a double sum over all the visibles and all the hiddens. But this Q of V doesn't have an H in it. So basically that Q of V is the marginal over all the H's. So it's adding up over all the H's, Q theta of V, whoops, wrong. Like that, it's a marginal. Okay, so I'm going to call these two pieces L1, this is L1, and this one's L2. And I see now it's joke time. Before you criticize someone, walk a mile in their shoes. That way, when you do criticize them, you'll be a mile away and you'll have their shoes. Okay. Now let's look at the L1. We want to minimize this thing, so that we're going to need the gradient. We're going to be doing gradient descent. So let's get the gradient of that thing. And we're going to need the gradient of L2. Now I'm going to skip some steps here. Some of them can be tricky. So we're not going to cover the derivations of these. I'll just instead say that the gradient of L1 with respect to parameter theta can be given by the expected value of negative gradient of E with respect to theta. That's the energy. Evaluated, the expected value is evaluated over Q of H given those fixed visibles, the sort of scripty Greek V. So this is a distribution of H conditioned on V. Of H conditioned on scripty V. Okay, expected value. So we fix the visibles to whatever the input is that we're given, and then we want to evaluate the expected value of that gradient. We'll evaluate the gradient of E in a minute. This other one, L2, is a little more free form. It's expected value of the gradient of E. I'm not sure why I have a positive in one and a negative in one. There's probably a reason for that. I hope it's not a typo. The expected value of the gradient of E, but over a different distribution. It's the joint distribution of VH. Okay, so what is the gradient of E with respect to theta? So let's consider a particular parameter, W, weight, from I to J. Now recall, this is our energy function. I'm a bit bothered by the fact that there's a minus sign of one and not in the other. Well, we'll see. Okay. Looking at that energy function, if we were to compute the derivative with respect to Wij, the only place Wij shows up is when it's in the link between Vi and Hj. I guess it shows up twice actually. So I think there should actually be either a 1/2 in front of that energy, or we should get a 2 here. But I'm just going to ignore that. It's just a constant. Vi hj. Whoops, not vectors. Those are specific nodes. So see that this is with the supplied visible. Now this other one is not the supplied visible, so we put the sort of variable h and j. So those are the gradients of the E with respect to those weights for those two different scenarios. So therefore, the gradient of L with respect to weight Wij is, for this first one, Vi times Hj. This other one is Vi Hj. And I've accounted for the minus signs by flipping signs. See, they were just added together before, but now there's a minus sign in front of this one. Oh, and there's a minus. I think that's where this minus, somehow that minus sign, anyway, you can work it out. There's sign flipping, but it should be consistent. Okay, now let's call this first term 1, and we'll call the second term 2, and we'll address them one at a time. So for part 1, we're clamping the visible state. So how do we evaluate the expected value of script V I Hj over the distribution Q? So Q is our model, is our generative model. Our network is representing Q. So we run our network, and that gives us Q, the sort of distribution that we're drawing these states from. So by running the network, we can sample these probabilities. So since the V's are, in this first case, in term 1, the V's are fixed or they're clamped, we just have to fix them to what we're given, and all we have to do is figure out the expected value of the H's. So the expected value of the H's can be computed just with a single pass. You just take the V's, you project them into the H, figure out what the input to the H's are, run them through the Bernoulli, and get the probabilities. Those probabilities are the expected values. You could binarize them, like do the Bernoulli process, turn them into ones and zeros, but you'd have to do that, hundreds or millions of times to get a good idea of how often each node is on or off. Why not just take the Bernoulli probability directly? So that's what we're doing here. So we project those fixed visible nodes or clamped visible nodes up and get our input current for our hidden nodes, run them through logistic function, and that gives us our Bernoulli probability for our hidden states. So this is not really the hidden states. These are the Bernoulli probabilities. Bernoulli probs. Not to be confused with binary. Okay, so that's a nice little shortcut that we can get the expected value of VH that way. So the expected value of VH then would be this term here, the V that we're given, and the Bernoulli probability of the H's. So why is there a minus sign in front of that? Oh, because there's a minus sign up there. Yeah. Okay. So that's the first term. The second term is sorry, I skipped a step here. We can compute all those weights at once using a vector type, vector matrix sort of notation. So we take the whole vector, clamped vector V, transpose, times the vector of H probabilities, and this is an outer product. It's a rank 1 outer product. And it's going to give us a matrix that's M by N. That's the same size as W. Okay, I'll let you sort that out. But it should be, because it's the gradient of L with respect to W. So it better be the same size as W, because we're going to be adding it to W later on. Okay. Now on to term 2. The expected value of VIHJ over the joint probability of Q is this double sum over all the different V's and the H's, the probability of observing that VH state times VIHJ. So this is just expected value. So we could do this by Gibbs sampling. This is Gibbs sampling. We could run this net freely, not clamping anything, just run it for 100,000 sort of up-down passes and observe all these V's and H's and record them. Record how often we see each VIHJ outcome. So this is Gibbs sampling. Gibbs sampling. Run net freely and compute average VIHJ. In practice, it'd be more stable if you just ran it for 100,000 iterations of Gibbs sampling. In practice, they just do a single pass. Okay, so looking at this thing here, is that the first time I've introduced that notation? So here, going back to this thing, I don't really remember talking about this plot, so let me address this now. So starting with some initial state V naught, you project up and you get your H, your first H state. I'm calling H0. I might call it H1 later on. I'm not sure. We'll see. And then your H state, you project it down back to the visible state. Now you have a new visible state. There's all this Bernoulli sampling going on each time, right? You project V back up to H. You get your input currents, logistic function, sample that Bernoulli process to get this binary H, project it back down, up, down, up, down, up, down. This is how the network runs. And so that's what we're talking about doing here with this Gibbs sampling. You start with you could start with the visible, the scripty Greek-like visible that we're given. You project it up and then down. Of course, when you project it down, you're probably going to get a different visible state. That's okay. That's telling us something about our network, right? And you can project up, down, up, down, up, down, up, down, and count all the statistics of the VIHJs, the average value. But in practice, you project up. Now this is, we did this already in phase 1. We projected up to get the hidden probabilities. Now we can, after we've computed this thing over here, we can use those Bernoulli probabilities, do a sampling process to get binary, project back down to get a new visible state, do Bernoulli sampling on that visible state, and project back up. And this is called the recognition pass 2. And we use those two states, this V and this H, as a single sample from Gibbs sampling, basically Gibbs sampling with just one sample. And so we can compute them all at once using this vector matrix notation. And again, we can use the H probabilities. But we're using the actual binary V's. You have to use the binary V's because if you don't sample the Bernoulli process to get the binary V's, then projecting up doesn't work properly. Okay, once we have the binary V's, we project up and then we get the Bernoulli probabilities of the H's, and we can use those Bernoulli probabilities for the H's directly. We don't have to sample those. So to update all the weights, putting 1 and 2 together, we get this first thing here, where this is where we evaluate 1 in the clamped state, where we clamp that Greek V, we clamp the visibles, and then we evaluate the gradient of E that way. We talked about it before. This is 2, where we do the Gibbs sampling, but it's only a single sample. but it represents running the network freely. So ideally, when we project up, do that what we call a recognition pass, we'd get a hidden state. Then we project that hidden state back down. Ideally, that projecting down is called a generative or generation phase. We're taking the hidden state and regenerating an opinion of what the visibles should be. Ideally, those visibles should match what we started with. So you start with some visible, project up to hidden, project back down. Ideally, we'd get those visibles back again. In that case, that model would be doing a really good job of maintaining or representing that visible in the state of the hiddens. And so the hidden state can be used to regenerate the visibles. So this process of projecting up and down is basically measuring how far off we are from that ideal. So this strategy is called restricted Boltzmann machine learning using contrastive divergence. So we're basically running the network, and we're seeing when we go up and down as we run it, do we diverge away from the solution that we wanted to be held stable? Because if it was trained perfectly, you put the visible in, you get hidden, and you go back down, you get the visible back again. You can go up and down as many times as you like. There might be some variation due to just the Bernoulli sampling. These are stochastic neurons, but it should stay in the neighborhood of the solution that that's consistent with the visible that we put in at first. It should stay in the same region. So here's how contrastive divergence works. The algorithm is based on a comparison between the original input and how well it can be reconstructed from the resulting hidden layer state. So first is the recognition pass. So let me give some parameters here. Let's say that we've got m visible nodes. I know I gave these before, but I'm just reminding you. N hidden nodes. Okay, first recognition pass, we inject the visibles from our data, from the world. We observe one of the visibles and we clamp the input and we project up to get our hidden probabilities. So the probability of observing hidden state given our clamped inputs is sigma of the energy gap. So I'm putting in a vector thing over the energy gaps because it's the energy gaps for all of the hidden neurons. No, it's a script V. So input current, run it through the logistic function to get the Bernoulli probabilities. Okay, so once we've done that, we have now the probabilities of our H's. We can compute the first term in the clamped thing. So I'm going to say S1. S1 is going to be the co-occurrence statistics. It's just a name I came up with. You're basically counting how many times H and V are both on simultaneously. And I'm saving it in S1. So it's V transpose times the hidden probabilities, the Bernoulli probabilities. And this again is an outer product. So this thing is an element of Rm by n. So it's the same size as W. Okay, so now we've got the first term. Now we project those H's back down, but before we project back down, we have to sample H we have to sample the Bernoulli process for the hidden nodes. So we sample H to come from this Bernoulli process. And that'll give us a vector of 0 and 1s. Bernoulli. Okay, so once we have that, we can project down and get the energy gap for the visible nodes. Right, so we're taking those hidden nodes and we're projecting down. Now we compute the Bernoulli probability of the visibles given the hidden. I'm calling those hidden, the binary hiddens H1. Right, run through logistic. Now we sample those visibles. Sample to get V2. Yeah, see, I was using V naught and V1 before, now I'm using V2. It doesn't matter. I think you get the idea. It's going to be drawn from the probability, this Bernoulli probability of observing V given H1. And again, now this will be a binary M vector Bernoulli sampling. So now we've projected down to get the V2. Now we do another recognition pass, project it back up again. So we get the energy gap for the H's. It's negative V2 times W plus C. Right? And now H2 is, I'm saying to sample it, but before I said you don't have to sample it. So let's just say here that you could sample it. Sure, I'll just say we sample it, but we might just use the probabilities directly instead of sampling the Bernoulli process. Okay. I'll just say that, or use sigma directly. Okay, so we compute the co-occurrence statistics again, right? Because we now had a V to H recognition pass, so we can look at the correspondence between those two states. Co-occurrence stats. We'll call it S2. It's going to be V2 transpose times H2, whether that be the Bernoulli probabilities or the binary sampled Bernoulli states. And again, it's an outer product. Great, we have S1 and S2. Those are basically those two terms, the term 1 and term 2. So we update the weights. W new is W old, the weights, plus kappa times S1 minus S2. Y plus. Well, obviously, but you can switch the sign by switching the S1 and S2. So you can make it minus kappa times S2 minus S1. I'd have to look at my code to see which is the right one. According to this, why did I switch that? So there's a minus sign here. Minus L1, minus L2. Again, okay, these are just signs. I apologize if I've flipped a sign somewhere. I reworked this. I've given this lecture before a few times, but I reworked it quite a bit this time. So, and one thing I did is I switched some signs. So I hope I didn't screw anything up, but let's just go for it. Okay, so that's how you get the updated weight matrix. And you can do the similar thing for the biases. Similarly for biases. So B new is B old. Now I'm saying minus gamma V minus V2. So I'm using the V's directly. You don't need the co-occurrence statistics for the biases. You just look at basically how often the visibles are on versus off, and that gives you the bias. For the visibles and for the hiddens, same idea, except you look at how often the hidden nodes are on. H1 minus H2. So I just say note minus sign. Okay. So as with other methods, you can process a whole batch. The way I've written these formulas is you can compute a whole batch at once. These outer products that we have over here are the right thing. So you could process, whoops, I think I just undid one too many. You could process many samples, and V will just have a whole bunch of, in V you'd have a whole bunch of rows, and H would have a whole bunch of rows. So when you multiply V transpose times H, it adds up over all those multiple samples, and you get multiple samples contributing to your co-occurrence statistics. Okay, so as an example, and I'll run some code in a minute, let's just say our universe, as our agent is walking around, the things that it observes, it's got three, in this case, in this example, we have 3 visible nodes, 2 hidden nodes. So the world could contain 8 different visible binary inputs, but this world that this particular agent is walking around in only sees 0, 1, 1, 1, 0, 0, and 1, 1, 1, only those 3. And so because those are the only visible states it really needs to focus on, it can represent those 3 states in its 2 hidden nodes. So it can come up with a binary code to represent these 3 things. With 2 hidden nodes, there are 4 different hidden states. So that's enough encoding resources to encode or represent this world that has 3 different visible inputs. So when I run this, starting from random weights, you see I get a whole bunch of, like the energy can be quite low for a whole bunch of different states and quite high for other states. And the visitation frequency is kind of all over the place. Now, we want to train it. So let's train it by going through this sort of loop process where it's called simulated annealing, where you turn the temperature down as you go. And that basically, at first the temperature is high, so it allows things to move around a lot and sort of try to find sort of general agreement and like lower energy regions. And then we progressively turn the temperature down and down, so it's basically getting more and more frozen, and can, instead of bouncing around trying to find a global canyon in the energy landscape, it can once it's in that canyon, it can now turn the temperature down and find like the lowest points in that canyon. So for each temperature, T equals, I could do 20, 10, this is just an example, 5, 2, 1. It really depends on your data set. So for each of those, we're going to go through this learning process. So for each of 400 epochs, so we're going to go over whatever visibles we have. This is specific to my really toy data set. I mean, I don't even know if I use these particular numbers, but it'll depend on your data set. So I've got a small data set. I guess I go through a whole bunch of times. So for each epoch, we choose a batch of visibles for each V batch. So I'm calling that visibles. So these are visibles that we've got in our data set, so they're relevant. They're the ones that occur in the world. So first thing we do, and I didn't really talk about this, but we can add noise. We can sort of jitter the data set, optional. That can help to stabilize things, but I won't dwell on that. Now, what we do is following this contrastive divergence strategy, we project up the visibles up to the hidden. So we go, maybe I'll do it this way. Visibles go up to hidden states, H1, and then we collect S1. Then we project down and up again. So H1 goes down to which I'll call capital V1. I called it V2 before, whatever. Back up to H2, and then again we collect co-occurrence statistics, which I'm calling S2. And now we've got our S1 and S2, we can do our update weights. Update weights and biases. Obviously you'd need to keep in memory your V's and H's to update your, well, I guess you have to calculate, summarize your how often your V's and H's are on to update the biases. Next batch, and then next epoch, and then the next temperature. Okay, so after all that training, in this example, the energy profile looks a lot different. We only get 3 different states that have really low energy. And when I run the network freely, those states are occupied far more frequently. And I won't go into, which index counts for which particular visible and hidden state. Instead, I'll represent that down here. It's a 2D, I said 2D surface, but it's actually a 2D whatever stem plot. Let me label these. This axis over here on the right is the hidden axis. It goes from 0 to 3. And so this element here, the value of 0, represents 0, 0. This here is 0, 1. And this one over, then it's 1, 0, and then this one here is 1, 1. Over here, so this is the hidden states. Over here is visible. This first one is 0, 0, 0. I'll just label the ones that are relevant now. This one here, where we've got this peak, that is value 0, 1, 2, 3. So it's 0, 1, 1. Yes, 1 plus 2 is 3. This one here is 1, 0, 0. And this one here is 1, 1, 1. So if I'm not mistaken, if things, well, I mean, this is a pre-computed example, so it better be right. Oh, that's, yeah. These 3 things where we have these high peaks, these high stems, correspond to the objects in the world that were common. So 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, and 1, 1, 1. So it's learned to observe those and encode those in a network state that's stable and low energy, visited frequently. So using this strategy, let me jump to the code now. So here's this code. It basically just runs a version of what you just saw, but using a new set of random weights. So I've got the same set of same set of visibles in my world. So I'm going to create a random restricted Boltzmann machine and evaluate it before training. So before training, you can see the energy is low and high in different places. The blue is the actual visitation frequency from Gibbs sampling. I just run the network and count how many times I occupy each of the different 32 states. This red I've added here, oh, it's mislabeled, sorry. It's actually the soft max of the negative energy. So if you look at the energy, the Boltzmann distribution is basically a soft max. And so if you evaluate the Boltzmann probability from the energy, you get these red dots. For a particular temperature, you have to adjust the temperature to get it to match up to the blue dots that I observed from my Gibbs sampling, but you can see they follow the same pattern. And as a 3D plot, you can see that there's all sorts of states that have high visitation frequency. Interestingly, if I evaluate the visitation frequency, like this is a scatter plot of log of visitation frequency, and negative energy, you can see that energy and visitation frequency are highly correlated. Not necessarily linearly correlated. They're not linearly correlated, but they're related. So now let's train it. You can see I've got a bunch of, I've got a temperature profile where I turn the temperature down progressively. 2,000 epochs, it's all pretty quick. So after that first stage of training, you can see the profile of states is quite different. I've only got 3 states that show up a lot, and it looks like this. And I'll run one more batch of training at a lower temperature to try to, I mean, it did a pretty good job already, but so now this is, you can see that only 3 states are visited frequently, and again, you can, it's just another view of it that matches what I just discussed in the handwritten notes. So let's see what the hidden states are for the different inputs. So I've got the stimulus holds the 3 different inputs, and I run it through my network, and I can see that 0, 1, 1 maps to a hidden state of 1, 1. 1, 0, 0 maps to a 0, 0. I'm rounding them, by the way. They're probably pretty close to 1s and 0s anyway. And visible state 1, 1, 1 maps to 1, 0. So it's come up with a different binary encoding for the hidden layer for each of the different inputs. So now let's set those hidden states to the binary, these 3 different binary states, and project down to see what visibles we get. Now this is not rounded. Well, it's rounded to 4 digits. Was that rounded to? Oh, it was. This one up here was rounded to 4 digits, so it was really close to 1s and 0s. Here we can see when we put a hidden state of 1, 1, it projects to 0, 1, 1. And when we have a hidden state of 0, 0, it projects to 1, 0, 0, and etc. So this is basically the opposite mapping of the one above. So this network has really learned this model to encode and reproduce this data, this world that it sees. So going back to the lecture notes, this is how we can train a network one layer at a time. So you basically feed in one layer and you train the hidden layer above it to come up with an efficient representation of that world, or of basically come up with a model of the data that it sees in the world. After you've trained one layer, now you can basically depend on that hidden layer. So when you put inputs in, you know that your hidden layer is going to be something efficient, or a high fidelity representation of the visibles, and you can now use that as the visible for the next layer. I won't draw all these connections in, but you get the idea. So this is called a deep belief network. And then once you train multiple layers of a deep belief network, the very top layer is going to be some binary pattern. So for a given input, the top layer is going to be some binary pattern that sort of re-represents that input. And if you want, if it's a classification problem, you can have some one-hot targets on top of that, and then train a single layer just using backprop to classify those binary patterns into the classes that you want. So the restricted Boltzmann machines had a pretty big impact. Early on, when people were playing with neural networks, it was really difficult to train deep networks because of the vanishing gradient. People didn't have enough data. They weren't necessarily using the right activation function, so it was really hard to train deep networks. This was a way to pre-train a network to sort of come up with really good, sort of solid, hidden representations of your data. And so if you train a few layers using RBMs, then you could take those pre-trained things and start doing backprop. And the backprop would be less susceptible, far less susceptible to vanishing gradient, because you've already come up with decent representations in your hidden layers. So it was it was a big deal pre-2012 for pre-training deep networks. Then there was a Netflix competition that was in the early 2000s, where basically it was all about recommender systems. So given what movies people have seen, this is back when, like back before streaming, when Netflix was actually by mail delivering DVDs to people's houses. That's how Netflix started out. Now it seems ridiculous. But it was a big investment to send someone a DVD. So they would send a DVD to you, but you didn't ask. You don't say which ones you want. I don't think so. It would often just send you ones it thinks you will like. And so it had a lot invested in trying to predict a movie that the people really like, because they're investing in the mail. And so they had a big competition where they give $1 million to whatever whoever could come up with a really good recommender system. So deep belief networks were a front runner for a while in this Netflix competition. And of course, Geoff Hinton won the Nobel Prize in 2024 for this work on restricted Boltzmann machines.